So, so we are going to see, for example, for Dirac, remember, clean Gordon equation, clean Gordon Schrödinger equation, वो जो फॉर्म है for free scalar, so इसका form will be more or less phi is 0. If you want to, if you remember, if we want to make its what I should say, how Dirac arrived at negative probabilities of doing away with positive probabilities, जब हम इसको Schrödinger equation को we have sort of equivalence with the equation of continuity, where some of the terms, for example, if I write this psi square minus, once we solve Schrödinger equation, this is minus. So we want to make thus इसका equivalence with the continuity equation. So this term and this term. यहाँ इसे हमारा था ना when square of this thing. So it will have plus and negative minus. So Dirac was not comfortable with the negative probabilities. So उसको करने के लिए उसने वो differentiation को second order को linear से he just whatever modification he did. Such that जो हमारे पास रो है, for example रो का form ऐसे रहेगा. Imagine size का dV and current density is so you can say जो हमारे पास wave equation है which was later shown by so the point is जो हमारे पास rho है so for Dirac rho must be not proportional to twice imaginary pi diagonal d phi by dt. So if I write it 8, I can write it 8, I can write it 9. So this is equation of continuity. So you can see this way. So in the similarly, जो हमारे पास जो second quantized value, so sort of files को in terms of हमने operators को लिखा था, ठीक है? So it was phi of xt was basically ak exponential of iota k dot x minus iota mu kt minus d divided minus k exponential of it must be proportional to pi diagonal d phi by d, and it should not be necessarily a positive quantity. And rho का form हमने you can also take rho का form. You can take rho can also be d phi by dt phi diagonal minus d phi diagonal by dt into phi. This term. Then इसका for you can see this. If you want to write it for this. अब हमारे पास ये जो स्पेस इंटीग्रल है ऑफ ऑपरेटर विच कैन बी इजीली कैलकुलेटेड टू बी स्पेस इंटीग्रल कैसे कैलकुलेट करेंगे इस तरह हम कहते हैं चार्ज डेंसिटी, है ना। अब इसमें ये है कि जो वेव फंक्शन का स्टेट साई, इसका एवोल्यूशन इन स्पेस कैसे होगा, विच इज बेसिकली गिवन बाय श्रोडिंगर इक्वेशन। बट अब हम इसके सॉल्यूशन निकालते हैं। इसका कोई भी है ना क्लासिकल स्ट्रिंग, उसके सॉल्यूशन निकालते हैं। दिस इज एन मोड, एन इज 1, एन इज 2, है ना। फिर एंटी नोड कहाँ आएगा, नोड कहाँ आएगा, do all sort of exercise. So we are going to do the same exercise for this relativistic equation, relative plane order Schrodinger equation. उसी का फॉर्म हमने कहा फिर इस डिराक इक्वेशन, इसका सॉल्यूशन इन सम फॉर्म रो को हम इन डिराक सॉल्यूशन में भी did those modifications of changing the second order differential equation to first order differential equation. जिससे जब हमने कहा था iota h d psi by dt is equal to h psi. H is the Hermitian matrix. वो matrices उसके 4 forms हैं. So how we did the exercise of changing that differential equation to the first order differential to do away with the negative probabilities. So you can have this. So in the same way you can see इसका जो ये है operator can easily be calculated. Now since we have written 5 in terms of these operators, A and B diagrams in those spaces, so we can write it as A dagger K, A of K minus B dagger K, B of K, and has eigenvalues of either sign. अब इसमें यहाँ भी प्रॉब्लम आ रही है कि जो आइगन वैल्यू है हमारा फॉर आइगन वैल्यू फॉर सो जो डेंसिटी ऑपरेटर हमारे पास साइड एगर साइड है ना, साइड एगर साइड दिस there are introduced state is a positive quantity. But in order to construct a physical density, we ought to subtract the contribution of filled electron states. For example, in order that this thing should come out to be a positive quantity. In the principle, हमारे पास दोनों values आ रहे थे. Positive value भी आ रहा था, negative value. So Dirac was not comfortable with the negative. So positive value लाने के लिए हमने we just rho को इस form में दिया, and then we wrote the same equation in terms of these operators. Phi का form लिखा in terms of operators. अब ये क्योंकि problem appears for particular spin operators, how we just give values which will come out to be positive if we have written these phi's in terms of these operators that we ought to subtract. So we हम ऐसे करेंगे, and the number of operator को हम ऐसे d3x is d3 side agar side, है ना, side agar side is the normal probability of x not only 1 but it will only be plus 1. And if you are to write it for this thing, EK, BK. So the anti-commutation. So अब if you remember हमारे पास जो A's and B's है ना, इनकी commutation relations भी हैं and anti-commutation relation. तो उस हिसाब से हमारे पास वो bracket commutators आ रहे थे, 4 फॉर्म. अब ये है कि how to assign signs to those commutators. कौन सी properties which we have introduced here as a commutators which will be suitable. Such that हमारे पास value जो आएगा वो negative नहीं आना चाहिए. That's our choice. We did away with negative probabilities with the particular value of rho. In the same way, once we translate those equations in terms of creation and annihilation operators, the use of commutators in a way which will do away with the negative signs. So हमारे लिए वो problem बनती है, ठीक है? So for example, the anti-commutation relations of these allow us to rewrite this as. So it is itself an exercise. So कैसे होगा? It will also take care of it. So we have to rewrite it like this, so that we will not get negative sign. इसको rewrite करना है. N minus n side that this is for and this is for annihilation operators. ये n naught जो हमारे पास है n naught is a constant. You can see that. So n naught is a number in particular in vacuum. कुछ number है vacuum में, ठीक है? Because these are states, both. You can the annihilation and creation operators, operating constant states, which will give holes or which will give electrons in that vacuum. अब ये है कि जो n naught अगर constant रखेंगे in a particular vacuum, constant रखेंगे. अब इसमें दो arguments हैं. So we have been using the whole history of quantum fields. If you are studying its Jordan Pauli algebra, Jordan Heisenberg algebra, in Oppenheimer, these are different ways. अब in the same way, अब जो constant है, जो यहाँ रखा vacuum state, so that it should be constant or it should be positive. तो Fury and Oppenheimer का argument ये है, the reason can be both negative and positive eigenvalues for just spin zero. So हमारे पास spin zero particles, spin one particles, so on and so forth है. So for them, so we कह रहा है कि इनके लिए both positive and negative हो सकता है, ठीक है? एक और solution neither psi का वैल्यू neither psi of Fury and nor जो इन दो साइंटिस्ट ने Fury and Oppenheimer ने psi लिया वैल्यू और phi का वैल्यू लिया Vyskov and Pauli ने. They also took so they also wanted to define things in a way which will have positive probability density. To make consistency with the Dirac's argument, the probabilities should not be negative. In that sense, जो ये हमारे पास have translated the equation in terms of commutators, तो इसका value should be come out to be positive. But it turns out once we have those its commutation and commutation relation, positive नहीं आता, sometimes minus plus आता है. So how to do with the various things? तो कुछ लोगों ने कहा for spin particles it should be positive and negative, ठीक है? For Bohr इन्होंने ये argument की in that sense. अब इसमें जो argument है how people did this, उन्होंने कहा कि जो Hilbert space है basically infinite dimensional vector space. अब इन प्रिंसिपल जो क्वांटम मैकेनिक्स में हाउ वी रिलेट ऑपरेटर्स ऑपरेटिंग ऑन सम स्पेस, उसकी हम एक मैथमेटिकल एनालॉजी देते हैं हिल्बर्ट स्पेस से. अब हिल्बर्ट स्पेस इज इनफाइनाइट डायमेंशनल वेक्टर स्पेस, वो उसमें जो बेस वेक्टर्स हैं ना, तो विल टेक दीज क्रिएशन एंड एनिहिलेशन ऑपरेटर्स एक्टिंग ऑन दैट वैक्यूम स्टेट्स व्हिच विल गिव पार्टिकल्स एंड एंटी पार्टिकल्स थ्रूआउट, ठीक है? अब द आर्गुमेंट गोज लाइक दिस, वी से दैट Hilbert space is spanned by states defined as containing definite containing definite number of particles or antiparticles. Okay. So we have defined this space which is containing of particles as well as
antiparticles.
and phi n is a complete orthonormal state. तो फिर हम क्या कहेंगे and if phi n is complete orthonormal set of such states, then a measurement of particle number in an arbitrary state will yield a probability of finding a system such that the probability हमारी होगी it's basically phi n and psi n. So it's एक हो गया ना side हम लेते हैं अब क्योंकि हम particle we are defining particle Hilbert space in terms of particles and antiparticles. We can define जो उसका probability amplitude होगा in terms of phi's and size particles and antiparticles. अब इसमें ये जो phi and psi है, phi psi are not probability amplitudes at all, but operators which create or destroy particles in various modes. ठीक है? अब एक despite these whatever arguments attempts of theory did not immediately supplant उन्होंने whole theory में कुछ addition नहीं बताया so there were these field theoretical ideas and whole theoretical ideas जो मैंने start कर रहा था but in the meantime जो for example so we could by doing these things we could make certain calculations in the particular scheme. ठीक है? Some calculations we could do in this whether it was whole theory or whether it was Dirac. So the calculation here, for example, so lowest orders in powers of E square. So you could have, for example, E plus E minus. It was given by Dirac. E minus plus E minus is given E minus plus is given by Molar. The 30 की calculation in 1932 की. E plus E minus plus Z, E minus plus gamma plus Z, and gamma plus Z, E minus plus Z, yeah, E plus E minus, E plus E minus, 1936 की बराबर जी. So these were various what I could say reactions we could calculate via this whole theoretical methods. So इसका एक सक्सेस है. So in the same way, युकावा ने भी अपने हिसाब से एक फील्ड थ्योरी दी, which you might have studied in nuclear physics. वहाँ जो potential है, V R है ना, it was proportional to 1/r exponential of r. You can say these all attempts can be seen with these attempts of trying to understand this vacuum state, Dirac whole theory, how doing away with negative probabilities, and how we can then relate operators कैसे करें. अब इसका ये है कि इन होल ऑफ क्वांटम फील्ड की हमारे पास जो आता है with something called which I previously also said in the start of the lecture, infinities come out. है ना? What's how do infinities come in a given quantum field? But the coming of infinities is an old problem. ये इलेक्ट्रॉन में भी आता है. Electrodynamics basically the problem of infinities coming out, it comes in electrodynamics. ठीक है? But once we go for quantum electrodynamics, so the problem has continued there also. So whole problem of what I should say, for example, in electrodynamics हम क्या कहते हैं? Electromagnetic theory, magnetic theory. इलेक्ट्रॉन जो है will have infinite electromagnetic self mass, and the mass जो हमारे पास होगा it will be e square by 6 pi ac square, and for the surface charge distribution with the radius a tends to 0, ये blows up. फॉर एग्जाम्पल वो जो मैं कितनी बार कहता था, इलेक्ट्रॉन हमारे पास पॉइंट चार्ज हम लेते हैं ना, बट अगर इलेक्ट्रॉन का कुछ फाइनाइट मास, ठीक है, अब इलेक्ट्रॉन को एक जगह रखने के लिए हाउ इट विल बी, सो देयर आर अब्राहम लॉरेंस थ्योरी एंड अदर थिंग्स, सो एडवांस थ्योरीज, रिटार्डेड थ्योरीज, सो हाउ कैलकुलेट देम. सो फर्स्ट few terms में you get some infinities are coming up. For example, once you calculate a को हम, if it tends to 0, this term blows up. It becomes this. So अब ये है कि calculation of self energy, which is infinite. Later, once we study quantum field theory, there are various calculations: electron self energy, vortex correction. ठीक है? It's a whole exercise. People how they infinite problem को कैसे how we circumvent, solve तो नहीं करते हैं, इसको थोड़ा सा एक साइड से निकलते हैं, how we do away with it, or how we manage those problems rather than solving them. Yeah, इसी को अब in this context there are two sorts of what I should say divergences or infinities which come in whole of quantum field theory. तो quantum field theory को एड्रेस करने के लिए we basically want to do away with these infinities. इसी को हम कहते हैं regularization और इसी को कहते हैं renormalization. ठीक है? These are the different words for the same thing. So we are mainly interested in the renormalizable quantum field theories as compared to the non-renormalizable quantum field theories. Renormalizable quantum field theories are what I should say, they are finite and they are mathematically consistencies, or they are finite and it's as quantum field theorists it's we can deal with them in that sense. I mean में दो types of renormalizations how आती हैं. Before so the infinities come because of divergences दो हैं. क्या है? One is known as for example ultraviolet divergences. The second is infrared divergences. So they are divergences which arise in intermediate states containing particles which are having short wavelength. क्या है? And the infrared divergences ये आती हैं that arise from energies from low energies rather than higher energy part of integration. So the infinities which arise at the intermediate states यहाँ भी है with the short wavelength या high frequency means short scale पे जो divergence arise होती है ये होती है energies from lower energies या higher frequencies. तो ये दोनों divergences arise होती हैं in the perturbative expansion. We have when we expand, for example, electron self energy को we are seeing इसकी forward terms होंगी ना, first order, second order, third order, तो कौन सी terms diverge करेंगे और they don't define at some particular value of or a scale जो हमारे पास है, ठीक है?
Yes, sir. Diverge means if
a sort of pole comes or singularity comes, so you cannot define the function precisely in an analytical way. Mathematically divergent integral होगा if there is a function, है ना? There is some sudden there is cut. You cannot define a quantity here. ठीक है? फिर आएगा. There is not a smooth function नहीं होगा. अब यहाँ पर physically है divergence. You can define a physical quantity in terms of values, parameters. But at some point you are not able to उसको फिर वो नहीं होगा. You cannot extend it beyond that point. For lower energies, it may be infrared ultraviolet divergences if it has have higher frequencies, and if it's happening at higher wavelengths, lower wavelengths, it's infrared divergences. We'll do it in detail. कैसे हम do all of it in that sense. इसकी अपनी एक history है. For example, Dirac का for example delta epsilon he had this MC square. So he dealt with this sort of equations. जो Lagrangian है for example at higher orders, it comes out to be like this. So इसका अपना problem आता है E dot B. So how do we do this? So in this context, you can say we are basically enumerating the history of how things evolve in that sense. And in that sense, you can say, for example, Schindler maybe he calculated the calculation of magnetic moment of electrons. Which came out to be so in the same way artisan इसी का Feynman का भी है calculations we do S matrix or functional integral W in terms of और इसी तरह Dyson का भी है. Now we showed the unity of this Schrodinger's method and Feynman methods. So which I have first class थोड़ा बहुत इसके बारे में कहा है. So the point is that all these say So हम कहते हैं normally if I just use the words you need to find the QFTs which are renormalizable in the sense that infinities are reabsorbed into redefinition of finite number of coupling constants and masses. So this is how we do it. The idea is like QFTs which are in a sense the infinities are reabsorbed. Infinities are into the redefinitions of the finite number of coupling constants and masses. Interactions में हम reabsorb करते हैं infinities को. So that's a procedure. So you just have an idea of it so that you can formally go to this sense. Okay.